Hello everyone, welcome to lecture 6. In this lecture, I will talk about the second part of numerical linear algebra. Today, in this lecture, I will talk about matrix inversion. Just a review for matrix inversion. Consider that we have a matrix A with n rows and n columns, and we can say that if A is be able to invert row, then there is another matrix which is B with the same size of dimensions n by n, and then A times B, which is equal to B times A, which is equal to I, which is a identity matrix, which means that we have one on diagonal elements and zero other elements. So if we can say that B exists, then B is the inverse, and we can show B as a power of -1. So matrix inversion is the process of finding a -1 for a given matrix. Matrix inversion has a lot of applications. For example, in finding the normal distribution or multivariate normal distribution, you can see have a matrix inversion for covariance matrix here. And for another example, the solution for least square linear regression also has a matrix inversion in that formula. And also matrix inversion is a fundamental role in many computer graphic routines. And so as you can see, matrix inversion is so important in numerical application, for example, probability distribution function, or as I mentioned, algebra computation. So this is so important how we can compute matrix inversion in numerical algebra. So in this lecture, we want to introduce an algorithm for computing matrix inversion. So the algorithm that we want to talk about is to find matrix inversion is Gauss-Jordan Elimination. And this is a fundamental algorithm. Before that, we want to make sure, we want to introduce a simple version of this algorithm, which is a Gaussian elimination. And this algorithm can be used for solving this equation, which is A times X is equal to B, and A is a matrix and B is a vector. And we want to find the solution for the X in this equation, right? So Gaussian elimination can be used for this. And mostly the rules that we have in this algorithm can be taught as a systematic application of the simple substitution rules. For example, we need to replace some some row for another row in the matrix or something like this. And Gauss-Jordan elimination is the application of this idea. And instead of just having, for example, A times X is equal to B, we have AX, which is equal to identity matrix here, and instead of here we have X, which is a vector, but here we have X as a matrix rather than a vector, right? So if we can solve this problem with Gauss-Jordan elimination, means that X is the inverse of A, because A times X is equal to identity matrix, right? So let's start for the simple example in this algorithm. For example, we have A, which is equal to a matrix 2 times 2 times 2 matrix, like this. And our goal is to find the inverse of this matrix, which is equal like this. So so in this algorithm, at the first, we need to another form of the matrix A, which is the augmented form, and then we in the augmented form we have original version of the A, and then we concatenate this A with identity matrix here with the same size of the A. So when we apply row operation, we need to do that until the left side, which is equal to the identity matrix. So or operation that we need to do on the each row can be from these three options that we have here. For example, we need to scale a row by a non-zero constant. This means that we can scale a row with a positive or negative numbers, or we can add a scaled row to another row, and then we replace that with the original one. And also we can swap two rows. These are operations that we can use in this algorithm. Sorry. So if we can do that, if we can do this element, this operation, without getting a row of all zero on the left, then the right side will be the inverse of the matrix, right? And at any point of the algorithm, if we get a row with all zero, then we can conclude that the matrix has no inverse. So for example, here we have A, and then we concatenate the A to identity matrix here. So operation that we can do are scaling a row, adding a scaled row, or swapping two rows. So at the first, we get the second row and subtract this by 2 times the first row, right? So for example, if we multiply the first row by 2, we have 2, 6, 2, 0. And then we get the difference between R2 and 2 times R1, and then we replace that the result by the second row that we have here, right? As you can see, we scale a row, as I mentioned here, by a non-zero constant, and then we add scale row by R2 plus minus 2R1, and then we swap the result with the original row that we have here, right? So in the next step, for example, we can get the minus second row, which is 0, 1, 2, and 1, and then replace that with R2. And then we multiply second row by minus 3, and then we add this row to the first row, R1, and then finally we have the inverse of the matrix here. And then we replace that by R1, and then finally we have the inverse of the matrix. So here in this algorithm, I just show that how we can compute the inverse of the a matrix 2 by 2 and by Gauss-Jordan Elimination algorithm. And then in this algorithm, the input is the original matrix that we have, concatenate by an identity matrix. And the output is we have identity matrix in the left side, and then we have inverse of the matrix in the right side, right? As I mentioned here. So the output is left side we have identity matrix, and then right side we have inverse of the matrix. So if we have a matrix by 3 rows and 3 columns also is the same, the input is the concatenation between the original matrix and then identity matrix, and the output is identity matrix in the left side and then the inverse of the matrix in the right side. This is so important to keep in mind that we need to have some operation on the input to get the output, which is like this, which we have an identity matrix in the left, and then if we can do that, the right side is the inverse of the matrix, right? So if we cannot do that, if we cannot make an identity matrix in the left side, we cannot get the inverse of the matrix, which means that the inverse of the matrix doesn't exist. So in this algorithm, we need to first make sure that the elements on the diagonal are 0 in the left side, and then the elements on the upper the diagonal. For example, here we want to change 3 here to a 0, and then 0 to 0 and minus 1 to 0. And also we want to have 1 on the diagonal in the left side. So let's see how we can do that with Gauss-Jordan elimination. And in the previous example that I showed in the 2 by 2 matrix, we apply the step in the arbitrary order, right? So if you want to guarantee that the result can be generated in a finite step, we need to apply them in a fixed order. So in the Gauss-Jordan elimination, we have two for loop, and in the first loop, we want to make sure that the elements in the downside of the diagonal is 0, and then in a for loop we want to make sure that these elements are becoming 0. So for example, for each row that we have here, which is index k, from 1 up to n, we want to, at the first, we want to row with the highest value in the case column, and then we swap it with the case row, right? And then we subtract a scale version of the case row from row blue, and then the step row ensure that we have 0 below the diagonal. And then for the second rule, second for, we scale the row to the diagonal entry is 1, and then we subtract the scale version of the case row from the row above it, and then the step above ensure that we have 0 above the diagonal, right? So just keep in mind that we have two for loop, and then the first loop make sure that we have 0 below the diagonal, and then the second for is just to make sure that we have 0 above the diagonal. And we have a pseudocode for this algorithm, and as you can see, we have two for loop here, and the first one is like this, and the second one is just like this. So I have an example to show how this pseudocode works. So for example, in the Gauss-Jordan Elimination, we have these metrics, and then we want to compute the inverse of these metrics. So at the first, we concatenate the identity matrix to these matrix that we have here. And then we have the for loop at the first, and then we apply each step to this input to the algorithm. So at the first, we consider that we just have, you know that in Python, the index of the matrix are 0 based, but here I just start the index from 1 to make it more clear. So for example, here, k is equal to 1, and then in this line, we want to find the maximum, the absolute maximum value that we have in column from k up to n, right? So because the k is equal to 1, and we want to find the maximum absolute value that we have in the column 1, which can be the first row or the third row, but doesn't matter, you can choose one of them. So in this case, I choose the first row as the maximum value that we have in the first column. And so in this case, I star is equal to 1, because the first we find the maximum value in the kth column, which is the first column in the first row. So I star is equal to 1. Then we check that this element A, I star is equal to 1, A1 and K is 2, A1, 2 is equal to 0 or not. So A1, K also is a 1, so A1, 1 is 2 and it's not equal to 0. If we find that this element is equal to 0, we can conclude that the matrix is not invertible. Other than we just need to go to the next slide. So then we swap rows K and I star. So here I star is equal to K, and if we want to swap row by itself, and we can do that, and then we have another for loop in this for loop that we already had. So for each row from K plus 1 up to N, which means that we need to compute something from the rows that we have below the K. For example, here the K is equal to 1. So we need to do something for second row and third row, right? Because K plus 1 is 2, and then up to N is equal to 3. So in this case, we compute coefficient factor, a scale factor here, which is F, is equal to AJK. So AJK, J is equal to 2, and K is equal to 1. So AJK is A21. A21 is the 1, and then divided by AKK, which means that AKK is 2. So F is equal to 1 divided by 2, right? So in the next line, we just get, we multiply the AK, which is the first row, by scale factor that we compute here, which is 1 divided by 2. And then we subtract AJ from this scale factor of the row, the first row. So AJ is equal to AJ, J is equal to 2, and A2 minus 1 divided by 2 multiplied by the first row, A1. So, for example, here, F is equal to 1 divided by 2, and then multiplied by the second row, the first row, which can be 2 divided by 2, or 3 divided by 2, 0 divided by 2. And then we subtract the second row from the first row, multiplied by 1 divided by 2. After that, as you can see, we change this element to 0. So we did that to make sure that this element is going to be 0, right? So we have another row that here, for example, row, the third row, and then for J3, we need to also compute the scale factor here, which is equal to a 3 1, which is equal a 3 1, which is equal to 2, and then divided by AKK, which is equal to A11, and A11 is 2, and then F is equal to 2 divided by 2. And then we get the subtraction between A3 minus A1. So after that also you can see these elements change to 0. So for this, now we need to go for the next step for this loop, and then you can see that k is equal to 2 now, and then we want to find the maximum value that we have in the second column for rows that we have below the k. Because k is 2, we need to just consider these two elements to find the maximum value that we have here. So I had a mistake here because we need to find the maximum absolute value, which can be this one, which means that the absolute value of minus 7 divided by 2 is equal to 3.5, and in this can be the larger than the 3, but I just consider that then by this their sign, and then I choose the third row in the matrix, but it's just a mistake, and then you need to keep in mind that you need to choose the second row here, because the second row has a maximum value. But I don't think that this mistake changed the final result. But so if we just consider that in this system the I star is equal to 3, and then I star is 3, and so A 3 2 is not equal to 0, so we cannot conclude that the matrix is not invertible. And then in the next line we need to swap rows k and I star because they are different, and then we just need to swap the second and third row here in this line. So because I assume that the maximum value here is minus 3, which is not true, so I just change the third and the second row here, and then we have another for loop, which can the j can be from 3 until up to 3, so we just need to compute these ones. So the scale factor here is 7 divided by 6, because A32 is equal to minus 7 divided by 2, and A22 is a minus 3. So this we can divide them and then f is equal to 7 divided by 6. And then similarly, we have subtraction for the A3 minus FA2. So this also can make sure that these elements change to 0, right? So because for the k is equal to 3, we don't have any rows below it, so we just need to go to the second row, second for loop that we have here. So in this for loop, we want to make sure that change the diagonal elements to 1, and also make sure that the elements above the diagonal are 0, are becoming 0. So for example, here, similarly for the first for loop that we had, but in a different direction, because in the first loop the direction was from k is equal to 1 to n, and then in the second for loop we have k is equal to n down to 1. So at the first, k is equal to 3, and then we divided row k, row 3, by A33. So A33 is a 1 divided by 6. So we just need to divide all elements that we have in this row by 1 divided by 6 to convert this element to 1, because this element can be 1 if we just divided it with itself. So as you can see, we divide all elements that we have here by 1 divided by 6. So in the second for, in this for loop that we have in this for, we, for each row j about the k, which means that j should be start with k minus 1 until down to the 1. We need to have a similar formula that we had here. At the first, we need to compute the scale factor, which is equal to a ajk. J is equal to 2 and k is equal to 3, so A23. The first we need to find that A23, which is equal to minus 1, and AKK is 1. So in this case, F is equal to minus 1. And then we need to subtract AJ by FAK, F times AK, and then replace the result by AJ. So A2 is equal to A2 minus, no, plus AK, which is A3. So in this case, we just need to replace the second row by value that we have here plus this value that we have in the third row. And you can see this element changed to 0, right? And then we go to the another k. Another j, because here the j was equal to 2, which was k minus 1, and then we go to j 1. So in the j1, a a1 3 is equal to 0. So scale factor become the 0, and then we just need to replace a1 by a1 minus 0 times ak. So for the k2, now we go to the k2, and then we make sure that this element change to 1. So we need to just divide every element that we have here in the a2 by a2 divided by a22. a22 is minus 3, and then we divided all element by minus 3. So I think the process is clear now, because we know that every line, we know that the intuition between for each intuition for each line here. So for example, here we just need to make sure that 3 is going to change to 0, and then 2 should be converted to 1. So in the next step, j is equal to 1 because k is equal to 2, and then j is equal to k minus 1. And then the scale factor can be 3 because we have 3 here, and then we divided by ak k, which is a22, and then the scale factor is 3. And then we replace the first row, which is aj, by aj minus 3 a2. And then finally, we have k is equal to 1, and then we need to divide each element in the first row by akk, which is 2, to make sure that the first element in the matrix is equal to 1. So now we have the identity matrix in the left side, and then in the right side we have the inverse of the matrix. So if you have any question about this algorithm, you can post on the Piazza, or ask the question in the office hour or QA session. But if you already know that why we are doing this line of the code, I think that would be more easier to find to find the step that we have in this algorithm. So we just need to keep in mind that the first loop is for making sure that the numbers that we have in the down of the diagonal is going to be 0, and then the second row, the second for loop is changing diagonal elements to 1, and then make sure that the elements on the above of the diagonal are 0. So let's go back to the main slides. So this is a silicon for Gauss-Jordan Elimination. And then if we want to find the complexity of this algorithm, at the first, we want to know that when you scale the row, so that it's diagonal is 1, how many multiplication do we perform? Or how many times do we do this? So for each row, if we need to have a multiplication, for example, we need to scale a row. So we need to do that with 2 times n, right? Because if we consider that we have 3, for example, 3, the n is 3, because we have another identity matrix here. So we have 2 times n elements here to compute the multiplication, right? So 1 per item in the row in the original matrix, and then 1 per item in the row of the identity matrix on the right. So we have 2 more n multiplication, right? And then we do that n times because we have n row in the matrix, right? Also, when performing a row reduction, adding one scale row to another, how many multiplication and adding do we perform? Or how many rows do we add row A to? So also we have 2 times n multiplication here, and also we have 2 n addition, because here we need to scale the all the elements in the row, which are 2 by 2 times n, and then we have 2 times n addition also here, and then we add the row I to all row below our row I, and all row above I. So we have do that to n minus 1. So if we need to compute the complexity of these algorithms, we need to compute all of these operations that we did, which are these operations are the basic operation that we have in this algorithm. So to compute that, the number of operations that we have in this algorithm are 2 times n squared for the first one that we have here, and we have 4n, which is the 2 times n plus 2 times n, and then we did that for n times, and then for each row, and then we have another operation for all row that we have for below row for this corresponding row, and then a row that we have for below above this row. So it means that we have n minus 1 also here. So we need just multiply these numbers to each other, and after some simplification of this operation that we have here, the number of operations that we have in this algorithm are minus 2n squared plus 4n cube, which is equal to big O, not big O in cube, which means that the complexity of this algorithm is n cube. So advanced matrix inverse algorithms are more efficient than these algorithms. The complexity of these algorithms are between n square and n cube, which means that we can do the inverse. We can find the inverse of the matrix more faster than the Gauss-Jordan algorithm, and then but because we are working with NumPy in this course, we need to know that what is the complexity of the NumPy for finding the inverse of the matrix. So here, the algorithm used by NumPy is not well documented. So we don't know what is the complexity of that, but we can estimate that by running some cases on the NumPy and find the runtime of that. So we know that the complexity in the worst case is n cube, right? So runtime is almost estimated by c times n power of b, right? So if we know that the runtime of the NumPy is equal like this, we want to find the value of the b here, because if we know that the value of the b, we can show the complexity of the NumPy to find the inverse of the matrix. So to find this value, how we can do that, we just need to get a logarithm, log of runtime, and then we have log of c, and then we plus that b times the log of n, right? So, for example, the solution is just like this. We need to run a bunch of tests for different n and record the runtimes. So we get the matrix to the NumPy and get the inverse of the matrix, and we just compute the runtime of the this operation in the NumPy. And then we find, and then we fit the line to the logarithm runtimes of all run that we had, all tests that we have, and then by finding the slope of this line, we can say that what is the b in this equation. For example, we run some testing, and then we get the runtime, and then we get the logarithm of these runtimes, and then we fit a line on these logarithm runtimes, and then the slope of this line should be a degree of the polynomial, and then we can say that what is the b, and also c, what is the c. So in this case, with this solution, we can find the complexity of the NumPy for computing matrix inversion, and then mostly the b should be between 2 and 3, because NumPy is faster than the Gauss-Jordan elimination. And then we already know that the Gauss-Jordan elimination is that the runtime of the Gauss-Jordan elimination is n cube. and then the numpy is faster than Gauss-Jordan Elimination, so we can conclude that the b should be between 2 and 3. So we compute the inverse of the matrix, and then we want to show that how we can use in the linear regression. So in linear regression, we have some data, and then, for example, here we have x, which is x has n rows and n columns. So n can be considered as a n data point that we have, and n is the number of features that we have in this the design matrix. And then y is equal to the n length of the length of the y is n, and which can be a vector of real value that we have for each data point. So the goal is to estimate the real value that we have for each data point here by getting n features that we have for each data point. So the goal is to estimate the goal is to estimate y that we have here for each data point. So the linear regression model that we can have here is y is equal to beta times x plus epsilon, and epsilon is a vector of noise. And then we need to compute the beta here, because if we have beta, we can multiply beta by x to find the value that we have in the y. So this is a linear regression, and the solution for this is can be computed by maximum likelihood estimation. So maybe you already know that about the maximum likelihood estimation, but if we want to get estimation for the b as a beta hat, we can have argument of that beta times x minus y transpose beta times x minus y. So if we find the beta that can minimize this formula, we can consider it as estimation for the beta, and then use it in this formula to compute the y for the next data point that we get. So here you need to just keep in mind that the goal is to find a relation between x and the y, which is beta. Because beta, we can multiply beta by x to compute the y, which can be considered as a relation between y and x. So for solving this problem, you need to get a gradient with respect to beta, and then setting it to 0 and solve, right? So the result is just like this: beta hat is equal to x transpose times x, and get an inverse of this matrix, and multiply by x transpose times y. So as you can see here, we need to compute the inverse of this matrix that we have here, which is x transpose x. So we can solve this using just matrix inversion and matrix multiplication, and the advanced linear also you may notice that by getting inverse of x transpose x, and then multiplication it by x transpose multiplied by y, we can find the beta height. But the problem is that how we can compute this inverse, and also how we can compute the x multiplication, because they are so expensive in the running time. So you can find the solution for this part of formula x transpose x minus 1 x transpose, and this can be called by Moore and Ross pseudo inverse, and there are some algorithm to find to compute this part of beta hat by this algorithm. And as a part of assignment 3, you need to implement and comparing linear regression using inversion, straight inversion, and pseudo inversion algorithm. So you can see now why we need to compute or why we need to learn about the inverse of computing inverse of the matrix here, because we already know how we can compute the linear regression between data point and the real value that we have here by using this formula, and with this formula includes the inverse of the matrix, which is so important. And then also you need to keep in mind that the NumPy has some methods or function for linear algebra, which called numpy.lined_out. And the method that we can find in this submodule are inner or outer products or matrix multiplication, or you can find method for decomposition of two matrix if you already know about that. For example, eigenvalue or singular value decomposition. And also there are other methods for finding norm or rank of the matrix, and there are some methods in the NumPy to find the inverse of the document or least square, or also pseudo inversion. So just keep in mind, if you want to use NumPy to find the inverse of the matrix, that's possible because the NumPy has already with these methods. And major takeaways from numerical linear algebra is that if you continue to do numerical computing in your research or in your course, sometimes you need to use linear algebra computation. And also, this is so important to keep in your mind the approximation of the complexity of your algorithm, because sometimes you before doing some coding or implementing, you know that your algorithm is feasible or not. For example, if you need to do a linear regression with 1,000 instance, that's feasible. But if you have 1 million instance, maybe you cannot do that with the generic linear regression, and in this case, you need to consider different methods. And in most cases, you need to assume that n cube is runtime, and also that after deciding about the algorithm or estimation that you want to use, maybe you decide to use algorithm that are approximation of the solution, not the absolute solution. So in most cases, approximations are good enough in many cases. So this is the end, and then don't forget about asking question about the linear regression and then Gauss-Jordan elimination. And you also need to start working on assignment 3, because as I mentioned in the first, assignment 3 is hardest assignment in this course, and you need to start early on working on that to be able to ask question about the problem that we have in this assignment. So that's the end. Bye now.